Right. Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all the students. This is again DMM 1523 or DRM 1213 Engineering Materials. We are now in a chapter 3, which is new chapter, Properties of Materials. For today's topic, all of you should be able to explain and analyze the mechanical properties of the materials. And number 2, you should be able to differentiate different type of material of mechanical testing for each materials. Number 2, for the lesson objectives at the end of the semester, students should be able to analyze the physical properties of engineering materials and metal alloys microstructure, phase diagram, as well as heat treatment processes. These are the two major topics that we are going to look at today. Number 1 is mechanical properties. Number 2 is mechanical testing. And there are several types of mechanical testing that we are going to learn. However, for today, we are going to look at only on tensile test. So let's move on to topic number 1, which is mechanical properties of materials. So in this part, things that you're going to learn is on the stress and strain. What are they and why they are used instead of load and deformation. Number 2, we are going to look at on the elastic behavior. What loads are small, how much deformation occurs, what materials deform the least. Number 3, plastic behavior. At what point does permanent deformation occur? What materials are most resistant to permanent deformation? And number 4, toughness as well as ductility. We are going to look at on what are they and how to measure them. These are the terminology that is going to be used in this topic. Hopefully you familiarize yourself with these terms, and please read it again and again. Or if you still don't understand, you may also refer to Google or textbook in order to see the definition of each of this terminology. And if you refer to this table, it shows the relative mechanical properties of materials at room temperature, for example, strength, hardness, toughness, and stiffness. And if you notice over here, the value of those mechanical properties are decreasing from the upper materials until downward. Now let's look at on the elastic deformation or elasticity. Elasticity is the ability of body to resist a distorting influence and to return to its original size and shape when that influence or force is removed. Solid objects will deform when adequate loads are applied to them. If the material is elastic, the object will return to its initial shape and size after removal. If you refer to this figure, to this illustration over here, this one showing you a initial state of the specimen, and number 2 showing you a specimen elongated a little bit after external forces being applied on it, and number 3 showing a specimen going back to its original state or condition after the force being removed from it. So it means that elastic deformations actually is reversible because it can go back to its original form. And in elastic deformation, the load being applied can be either a linear state or non-linear state. Okay, so number 2 is plastic deformation. Plastic is the ability of solid material to undergo permanent deformation, a non-reversible change of shape in response to applied forces. And if you look at the illustration over here, this one, the initial condition, this one is after a load being applied on it until it reaches its plastic region. And once the load being removed, the specimen doesn't go back to its original form. And it means that the deformation is permanent. So that's why in plastic region, it also known as a permanent deformation. And another part in mechanical properties of materials that you need to know is engineering stress. Engineering stress refers to the applied load divided by the original cross-sectional area of materials, also known as nominal stress. And it can be divided into two types, which is tensile stress and shear stress. The formula is the same, which is force over area. However, the difference is that the direction of forces acting on area is different. For example, for tensile stress, the direction of forces acting on area is actually perpendicular or 90 degrees to the surface area. However, for shear stress, the direction of forces is perpendicular to the surface area. These types of stresses commonly found in many types of application. For example, this one in cable. So this is the free body diagram for cable. Once you have calculated the value of forces there, then you just substitute into this formula for tensile stress. And for torsion, for shaft will suffers a torsion load there, and from torsion, if you draw the free body diagram, there will be a shear force acting on the surface area there, which means in this specimen it will suffer shear stress. This one refers to tau, not sigma. This is a typing error there. Yeah? However, the formula is the same. It's still force. It is still force over area. Another example is for bridges over here, but then the bridge here showing that it suffers a compression load, which means the value of stress there is in negative value. Other than that, we may also found in pressurized tank or fish underwater or even human in underwater. For pressurized tank, if we take the specimen over here and draw a free body diagram, we can say that the specimen is actually suffering a biaxial tension because it has two direction here, which is in y direction as well as x direction. As compared to fish underwater, and this one is called as hydrostatic compression because once in underwater, the specimen will suffer forces acting on every single area of that specimen or fish underwater or even human. And other than that, you may also want to know on how to, the formula to calculate the value of tensile strain, lateral strain, or shear strain. And please remember that strain is always dimensionless. This is only, I would like to remind you that this is actually an introduction to strength of materials. And the more detailed parts we'll learn in strength of materials 1 or strength of materials 2 or even solid of mechanics. The other parts that we need to know in mechanical properties is Poisson ratio. Poisson ratio is defined as the ratio of the change in the width per unit width of a material to the change in its length per unit length. Or if I take an example of a rubber, for example, and I squeeze it or I pull it upward or downward, it will change in diameter, whereby it will become smaller. Same goes to its length, whereby it will become longer and thinner or shrink in sizes. So that will be the definition of Poisson ratio, the changes of dimension in diameter or in cross-sectional area as well as its length. So that's why the value is always negative, because it shrink in shape. The value will be between a range of 0.25 and 0.4. If Poisson ratio equals to 0, it means that the width of the material doesn't change when it is stretched or compressed. However, if the material is getting thicker when stretched, then the value of Poisson ratio will equals to 0. Again, the formula for Poisson ratio is stated as follows, and the ranges value of Poisson ratio is 0.2 until 2.4. For example, in stainless steel, you may find it with the value of 0.228, whereas for copper is 0.33. And the value of stress, the formula for stresses is sigma equals to P over A, and for strain is equals to delta L over L. Now let's move on to topic number 2, which is mechanical testing. To be specific, number 1 is tensile test. This figure here showing a typical tensile test machine and a tensile specimen. However, how do we prepare? Okay, before that, this is the machine that can be found in our lab in UMP. Is known, whereby it is known as Universal Tensile Machine (UTM). This is where the specimen being placed, and this one is load cell, whereby it apply loads to the specimen until it break or fracture. The specimens need to be prepared. It's either using any types of standard like AST, MGIS, ISO, and so on and so forth. And it can be either circular dot bone shape or flat dot bone shape. Well, it depends on types of standards that is going to be used. However, despite of any standard, the result, this is the typical result of a stress strain curve that is going to be obtained for that specimen. Other than that, you may also found a load extension data and stress strain data from tensile tests. In mechanical tests, there are mechanical properties that that are important for us to understand, which includes elastic modulus or Young modulus, yield strength at 0.2% offset, ultimate tensile strength or UTS, elongation at fracture, as well as reduction in area at fracture. Now let's look at one by one. Okay, and before that, I would like to explain on a stress strain curve over here. Well, if you look at this figure or this table, this graph, you may find there's two sections over here axis, which is elastic region and also plastic region. For elastic region, you may find this linear continuous line and also the dotted line over there. But for plastic, the parabolic shape over here. So, for example, if we take a specimen, then we apply a force on that specimen until this point, then we release it. We release the force. The specimen will go back to its original form following this continuous line, this linear continuous line. And then we increase a little bit the value of forces on that specimen until it reaches this point. Then we release the forces again. After that, it will go back to its original form by following this continuous line, this linear continuous line. However, if we keep increasing the value until it reaches this Y point or yield stress point over here, which is slightly before plastic region, then we release the forces acting on that specimen. This specimen will go back to will follow this line. However, it will have a, we call it as strength yield stress offset with the value of 0.2%. So it will no longer following this linear continuous line. Okay, so this offset, this yield stress offset will only occur once you give the force until the end of elastic region. If not reaching at this point, then it will follow the linear continuous line over here. Okay, so now after elastic region, it moves to a plastic region, whereby at this point it will start to elongate. It will elongate until it reach UTS, which is ultimate tensile strength. And beyond that ultimate tensile strength, it will start to necking until it reach fracture region, whereby your specimen is already break and can no longer be used. So these are the specimen or illustration of this specimen happens when the tensile tests are being conducted. This is the original form, and then until after point Y, which is in plastic region, you may find your specimen will elongate or deform a little bit after reaching point UTS. Beyond that point, it will start to have necking over here, and finally it will start to fracture. It will break at this point. Okay, so now let's move on to the mechanical properties of tensile test. Number one is elastic modulus or Young modulus. Formula for Young modulus is E equals to sigma over epsilon, and this is actually the Hooke's law, known as Hooke's law. If you refer to stress strain diagram or graph, the value of E can be obtained through its slope, which is actually in elastic region, and it cannot be found in plastic region. So the higher the value of elastic modulus, well, it represents the higher the bonding strength of that materials. And this table or this graph here showing you a Young modulus or different Young modulus for different types of materials, and you can say that diamond over here provide a the highest Young modulus among other types of materials, even though those classified under metal alloys, polymers, or composite. Number two is yield strength. Yield strength is actually refers to a last point of elastic region and exactly before plastic region. So it happens at that point, one load is being applied to it and then being released. So there will be a 0.2% offset yield strength exists on that specimen. So if you calculate the specimen by taking example of by assuming the length of the specimen is 2 inches, if you calculate it its length, even though you have released the forces acting on that specimen, there will be there will be an additional elongation of that specimen with this value 0.004 inches. So it will no longer be 0 inches. And this figure here showing a yield strength for different types of materials. You can see that metal alloy have the highest yield strength as compared to the other types of materials. Number 3 is UTS. It is a point where before it starts to necking and break. For metal, UTS occurs when noticeable necking starts, whereas for polymer, UTS occurs when polymer backbone chains are aligned and about to break. From this table, from this figure or graph, you may see the comparison for tensile tests for different types of materials. Number 4 is ductility. Well, if the materials starts to deform before it breaks, then that material is known as ductile material. However, if the materials straight away break once load being applied to it and there's no deformation or elongation happen to that material, it is known as a brittle. Even the structure of failure itself is different between these two. For example, for the ductile material, it will have necking before fracture. However, and for brittle, the fracture surface perpendicular to the stress. Number 4, okay, this is continuation for ductility, and this is how you calculate the ductility of the specimen. You can use either length or the area to calculate its percentage. And if you look at this graph here, ductile material will have smaller ductility, whereas for this one brittle material will have smaller ductility, and for ductile material will have larger ductility. Number 5 is toughness. Toughness refers to energy to break a unit volume of materials. And from this graph, it shows that ceramic have small toughness as compared to metal and polymers. Metal have large toughness and polymers have very small toughness. Other than that, you should also know resilience, whereby it refers to the ability of material to store energy. And this is only the introduction for resilience, just to make you know and aware material itself should also have a resilience. However, the detailed part of it you are going to learn in strength of materials 1 or 2 and also solid of mechanics. Yeah. Other than that, there's also true stress and strain that you need to know. Well, the formula is the same. The still stress, force over area, or the strain is the same. Original length divided by length changes length. However, the difference is only on the changing area with respect to time of the specimen at that load. That's why the value of area over here got symbol I over there. Same goes to this one because it changed with respect to time. That's why the value of true stress is always higher or greater than engineering stress. So you may also compare it with this graph. You see that the value of true stress and strain is always higher than engineering stress, because engineering stress is actually a theoretical part. And this graph here showing a different value of true stress and strain curve for different types of materials. You may find either stainless steel, brass, steel, copper, aluminium, and so on and so forth. So you see different types of materials obviously have different properties, and even though certain types of materials have higher hardness, it doesn't mean it have a high toughness. Yeah. Stress strain curve also may be affected by temperature. For example, if the temperature being added into the graph, it will raise the ductility and toughness. Number 2, it will lower yield stress and the modulus of elasticity. Number 3, it will lower the ultimate tensile stress. Number 4, it will lower the toughness of the materials. Even the rate of deformation also will be affected by the temperature. For example, if you look at this graph over here, the higher the strain rate, then the higher the value of strength will be. Yeah. And this table here showing a typical ranges of strain and deformation rate in manufacturing process. You may find different types of processes that can be found in the market, like code working, forging, forming, rolling, extrusion, sheet metal forming, and so on and so forth. And these processes actually produce different value of true strain, as well as different deformation rate. So we cannot say that even though the same material going through a different process, it doesn't mean it will produce same true strain or a deformation rate. Okay, now let's move on to example. Example number 1. Calculate the engineering stress in SI unit on 2 cm rod that is subjected to a load of 1,300 kg. The first step that you need to do is you need to convert the load to a force using SI unit. So formula is that F equals to MA. Substitute the information into the formula, then you should be able to get the value of force equals to 12.2753 kilonewton. After that, in order to find the engineering stress, which is sigma equal to F over A, just substitute all the information over there, then you should be able to get stress equals to 40.6 megapascal. Now let's look at example number 2. Still the same. The question asks you to calculate the engineering stress in SI unit on a bar 15 cm long and having cross section of 4.25 mm times 12 mm that is subjected to a load of 5,000 kg. The first thing that you need to know is convert the load to a force using SI units. F equals to MA. Key in all the information and you should be able to get the value of force equals to 49.05 kilonewton. Then using the engineering stress formula, which is sigma equals to F over A, finally you should be able to get the value of stress equals to 9.62 megapascal. Now let's look at exercise number 3. A tensile specimen of cartridge brass sheet has a cross-section of 10 mm times 4 mm and a gauge length of 51 mm. Calculate the engineering strain that occurred during a test if the distance between gauge markings is 63 mm after the test. So by using a engineering strain formula, this one, just key in the information or data given. Finally, you will get the value of strain 0.235 with no units. Yeah. Now let's move on to exercise number 4. A 0.5 mm diameter rod sample of 1030 carbon steel is pulled to a failure in a tensile testing machine. The diameter of a sample was 0.343 mm at the fracture surface. Calculate the percentage of reduction in area sample. While this one, you just use this formula. After that, just key in the information because all the data is already given. Then you should be able to get the value of reduction in area is equal to 52.93%. And for exercise 5, 6, and 7, please do it by yourself at home. You don't have to submit it to me. However, if you do understand, that you may refer it to me. It's either asking in a group or in Google Classroom, and I'll come back to you later on. Yeah. So please take your time to copy this example, this exercise. Okay, moving to exercise number 6. Please copy this exercise too. Actually, this example is very simple and straightforward. If you don't understand, then you may refer to our earlier lecture. And this one, exercise number 7. For this exercise, you don't have to calculate, but you can explain in words, or if you still want to include a calculation in here, you can assume the data. Okay, now let's move on to exercise number 8. Based on the table below, which has the greatest percentage reduction in area? Number 2, which is the strongest? Number 3, which is the safest? Number 4, which is the hardest? So I'll give you a few minutes to think the answers, and let's see whether you are correct or wrong afterwards. Alright, so let's see whether your answer is correct or wrong. Number 1, material B. The answer is material B because it will experience the greatest percentage error reduction since it has the highest strain at fracture and therefore is most ductile. Number 2, material D, because it is the strongest because it has the highest yield and tensile strength. Number 3, material E is the stiffest because it has the highest elastic modulus. The higher the value of E or elastic modulus, the stiffer the material would be. And number 4, material D is the hardest because it has the highest tensile strength. And please copy this exercise too, or this problem. Actually, this problem summarizing the one that we have learned for today. And you don't have to submit it to me. This one is just for your own understanding. Okay, please copy. Same goes to this one. Please copy this question and try to plot the graph on your own. And you don't have to submit it to me, yeah? Okay, so as a summary, number 1, stress and strain. There are size-independent measures of load and misplacement, respectively. Number 2, for elastic behavior, this reversible behavior often shows a linear relation between stress and strain. To minimize deformation, select a material with a large elastic modulus. Number 3, plastic behavior. This permanent deformation behavior occurs when tensile uniaxial stress reach sigma y or yield stress. Toughness, the strength needed to break a unit volume of material. And last but not least for today, ductility, the plastic strain at failure. With that, I thank you very much for your kind attention and time. We shall meet again in the next lecture. So if you do have any problems related to this topic, please do not hesitate to contact me either in group WhatsApp or in Google Classroom. With that, thank you very much and see you again in the next class. Bye.